Thank you very much. Well, I start thanking the organizer for putting this nice conference after and being able to do it after all the time that was postponed. So it was nice to come to this conference. And thank everyone for coming for this Journey Ergodicity session, the Journey Ergodicity trip. So what I will talk about very much related to what Wembo introduced. I will focus on one of the results Wembo said. And I will, my plan is like to give the idea of the problem, give an idea of the difficulties, and briefly mention how we deal with the problem. But I will I will skip many details for the sake of clarity. Okay. There? Okay, thank you. So just to remind the general context of this, here we will be working on a probability space and we will have a transformation. We will assume for now on that everything is measurable, invertible, and that everything preserves a measure. So whenever I write any transformation, we'll preserve the measure that we are considering. And for this talk, we will be interested in like several commuting transformations. So we will assume everything is commuting. In the end, I will briefly mention something that is not commuting, but for 99% of the talk, everything is commuting. So just to remind the definitions that Wembo said, in case someone forgot them. So, well, this is the classical definition of ergodicity. So we say that the sequence, here I write this definition with the sequence of transformations. We'll say the sequence of transformations is jointly ergodic if when we consider the multiple ergodic average along these transformations, we get the correct limit in L2. So the same as Wembo, everything, all convergences here will be in L2. So this is the joint ergodicity sequence. And just to illustrate or mention a few results, and here I'm stating this for the general setup of several commuting transformations. Many things are known in the context of a single transformation, and just to remind a few classical results, in 77, his paper Fustenberg showed that when the transformation is weakly mixing, then you have joint ergodicity for these linear iterates, and this is like nowadays a classical result and can be done in an exercise with of course with some parts guided parts, but it's a rather classical result nowadays. And the next improvement in this direction is the result due to Bergelson, where he showed that under the same condition that weakly mixing, you have something stronger. Whenever you have polynomials that are non-constant and whose differences are non-constant, then you have joint ergodicity property. And what is remarkable about the paper is, well, the result itself, but also the method that in this paper it was introduced, the PET reduction method, which it's like a very valuable tool that it appears in most of papers dealing with this kind of expressions, and it's very versatile in the sense that whenever the problem you have, you try to find a PET scheme that will help you with your problem. Okay, so this is in the case of this here. Everything is a single transformation. Let me mention a few more results. There is this result of Franzignackis and Krach that tells that joint ergodicity, but there is a necessary here assumption of total ergodicity of the transformation. That means that all the powers of the transformation are ergodic, and you have an independent family of polynomials. I think Chandong mentioned this result in his talk. And let me jump into much more recent things. This is what Costas showed yesterday in the afternoon, that you have, if you have a, sorry, here it should say D, if you have some Hardy functions that belong to a Hardy field of polynomial growth, I will comment later on names, so just to have in mind, just think of this as n to some 1/2 or something. So if the linear combinations are far away from polynomials, like log away from polynomials, then this is jointly ergodic. I missed some words there. And just to mention some results in this direction, previous result by Bergelson, Moreira, and Richter that Costas also mentioned in his talk. And well, they can deal with a bit more general functions that you can control. You don't need log control, but a function of the log, but then you have a weighted average. Okay, so all the results so far I have mentioned are for a single transformation. And so one could ask, what happens in the commuting case? And for people that have never worked on the convergence problems for commuting transformations, I have to stress that this is quite well, it's the similar question, but the methods are very are not exactly the same. It becomes a different question. So it's a different problem. For instance, we know we know by the work of Walsh that we do have, say, L2 convergence for commuting transformations and polynomials, but to the best of my knowledge, we don't have, like, say, a standard proof using the technology of semi-norms and characteristic factors. So even those cases are the cases of those averages haven't been like well established with the classical technology that's available for a single transformation. So this becomes a different problem. And here, let me mention a few results. Wembo already showed them, but just to put more context. So there, in this direction, there is also the result of Bern and Bergelson that showed what Wembo called the joint ergodicity problem. You have joint ergodicity as long as you have some ergodicity in a product space and you have enough ergodicity of transformations. And here, as we saw from Wembo's talk, the philosophy is that if you have ergodicity in the product space, well, you have a convergence to the right limit, but in the product space. And you want something, the ergodicity problem, you want something for diagonal points. So and the diagonal points have zero measure in the product space. So how to pass from something that is in the product space to the diagonal? And well, that's where all these conditions help. So that's basically the problem. And this was, there is this more recent result of Bergelson, Leiban, and Son, that they prove the joint ergodicity problem for functions that are generalized linear functions, say floors of AN, for instance. Okay. So we do have already some results in the commuting case. And I mentioned here also the results of Chu, Frantzigakis, and Host. This is in the polynomial case. And well, it can be deduced from their work that they can obtain some joint ergodicity result. But here the polynomials have this distinct growth, distinct degree. And what Wembo talked about was some recent development in the polynomial case. And there, well, some work with Ferre Moragues, Koutsogiannis, and Sun. And there are some interesting, very recent results by Frantsiginakis and Koutsa that I pronounced it right. That Boris will talk about, I think, later. So the question that I want to address now, it's okay, we have in the comparing the single transformation and the commuting transformation, well, we have several results for the single transformation, and for the commuting, we have a few results. So what else can we say about commuting transformations and other iterates? In particular, what can we say for sequences like the ones here, like the Hardy function? So that's the main thing I want to talk about now. And yeah, like what about non-polynomial function? So this is the main result I want to talk about. It's recent with Andreas Koutsogiannis and Wenbo Sun. And okay, I will be very vague here, and I hope to be less vague later. So assume that you have a system with commuting transformations, and let take be a good function. I cannot be more vague than that. So we have a joint ergodicity property if these two conditions were the conditions that Wenber proposed as the joint ergodicity conjecture. So you have some ergodicity in some product space, and you have some ergodicity of some transformations in the space. And that's the result. So what is good? Examples of good. Well, the examples by themselves don't tell much, but we'll comment later. So we can achieve this kind of examples, like Hardy field functions. This is has some oscillation. We can also deal with that, like this tempered part. And if you are wondering more about what kind of functions, I will comment on that by the end. But say for if you are impatient and you want it right now, we can do at least Hardy functions that have a strongly non-polynomial part that dominates the logarithm. And I will come back to this by the end. Okay. So this I will review very quickly because Wenbo already talked about it. So these are the host cross seminorms, or I would say more precisely the box seminorms, or box host cross seminorms. So we have a system with D transformations, and given subgroups, we can associate to the subgroup some seminorm constructed using this host-cross measure. And what we saw in the previous talk is that whenever we have, well, this is needs a proof, but it's I would say it's a fact, but it's a result. Whenever they act, if the groups act ergodically, then you can replace each of them by the whole action. And these are genuine host-cross seminorms. These are the ones that are related to nil spaces. We don't have a clear description of these seminorms if we don't have ergodicity assumptions. But these are the ones that appear when we deal with averages for commuting transformations. Okay, and here I will introduce a quick notation that I will use. If I put something times something, means that I will repeat that m times. That's a quick notation. For instance, if I write two groups, G1 and G2, and I put 3 times, I will repeat each one of them 3 times. I mean, I will repeat the set 3 times. Yeah. Yes, it is, but it's not like immediate. It needs a proof. But that is commutative for decommuting transformation. already appears in the paper by Bernard Host. But if you consider subgroups, it's the same. It's written precisely in a paper by Wembo. It can be proved. Yeah. So here I could put G1, 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 G2, G2, G2. Yeah, sorry. Yeah, that should be their equivalent. You mean this? Or yeah. Yeah, we need some ergodicity assumption. So the idea is that yeah, if not, it's false. But if you do assume ergodicity, it basically is because in the first step you define, for instance, if you have only two, you define it with respect to the invariant sigma algebra. And if you have ergodicity, will be the product sigma algebra, which will be the same as the whole group. Yeah. No, that's always true. Yeah. Okay, and so what we want, what I wanted to present is this result about the joint ergodicity problem. As Wembo mentioned, there is a very neat and useful criterion that was introduced by Franziginakis and then was generalized by Best and Ferrer-Moragues for for abelian groups. So here these are the years of publication, but where they appear in the journals. But Nikos proved this in like before. So this neat criterion is that enable to show joint ergodicity, you have to check two things. One, it's that you have good control seminorm, good in terms of the seminorms. So if you have a system and if you have a large host class seminorm that is 0, then your average is 0. And the other thing you have to check is the good, as Wembo mentioned, the good equidistributions in the torus level. So combining these two things, you can get joint ergodicity. So the ergodic, the assumptions we have in the problem allow us to, well, deal with this property. So the difficulty in the joint ergodic problem, it relies on this point number one, how to control a given average. So that's the main problem. So using the criteria, the main goal is to control this by some averages. So that would be the goal of the rest of the talk. How to control that in terms of host class seminorm or box host class seminorm. Okay. So here is the one statement that we got, is that if you want to show that this goes to 0, then it's obvious to, I mean, you have this seminorm control. If this seminorm is, you have T1 and the difference of T1 with the other transformations and repeat it many times. We don't have really, we could say something about the D, but it's not important for the application. Because in this criterion, we only require that there exists a mem. So we don't really care how big this can be big. It will depend on the PET induction and other things. So this is the result that will imply the joint ergodicity problem. And I will try to tell the ideas, the steps to get such a result. That will be for the rest of the talk. Yes, because Wembo showed in this talk how to use this in order to get to the joint ergodicity. Okay, so these are basically the steps to obtain the seminorm. So the first step is, so we have a problem here about iterates of a function, smooth function. And the first step is transform the problem into one of about variable polynomials. I will say in 1 second what is that. So this is exactly what Costas Sinas showed last yesterday. And here we followed this approach that was also developed by Franzikinakis and by Costas in his paper. And then we have to look for some appropriate PET scheme in order to decrease the complexity of the average we are considering, and then find some good estimates in terms of they will be average of seminorms. And this is for this third part is where we use what we have been developing with Wembo, Andreas, and Andreu more recently, is that in order to bound these averages of seminorms, we can use some tracking on the coefficients. That was what Wembo mentioned in the last minutes of his talk, and then use a concatenation theorem by Ziegler to get a single box seminorm that controls the average. And then the ergodicity assumptions will allow us to pass to a real Host-Krah seminorms instead of a box seminorm. Okay, so let's look at the first step. We will transform the problem into another one, and we will try to solve the other one. So what is a variable polynomial? A variable polynomial are sequences like this. You have polynomials, but they are indexed by some capital N. And this capital N will make this as a sequence of polynomials, but we will require that the degree doesn't change, but the coefficients might change. For instance, these are all variable polynomials of degree 17, and the coefficient is changing with capital N. Okay, so what is this useful for? It's when you have when you put the problem in this context, the sequence you want to deal with, the sequence A, this is what Costas showed yesterday. You can approximate locally this sequence A by polynomials, and the polynomials are the Taylor expansions of a given degree. So you approximate locally the sequence A by a polynomial. So here the R, it's so here we are approximating the sequence A like at N, and you look like a neighborhood of N. And you approximate this A with some polynomial that will depend on R, and where you approximate it, it's like a small interval. You approximate A in a small interval around N, and with some error term. So this will be the Taylor expansion of your smooth enough function. So what is this useful for? Here there is this is a result. So we prove it in a paper, but it follows some idea of Costas. Is that if you want to show that the average you were considering goes to 0, it suffices to show that this other thing that looks worse, it's 0. So we change this condition red by this condition blue. So at the first impression, this looks worse than this. So why you would make your problem more complicated? But it turns out it's not more complicated, because here you change the sequence A by some variable polynomials. Well, but you have some other terms, etc. But you gain a lot more by changing the sequence into variable polynomials, because if you have variable polynomials, we will be able to use some PET scheme and reduce the complexity there. So I wanted to remind that yesterday Costas mentioned that if one starts with here and tries to do van der Korput, then you may get to things that are not useful. So it turns out that if you first change the problem and then you do some van der Korput pet scheme, then this will be more useful. So here we gain in sense of understanding these iterates, this more, but we'll have to complicate it with some weight and some taking the supremum of our functions, but this will not be a problem. Okay, so first step, we change this by this other problem. And then the question is how to deal with this problem. So how to deal with this problem. And here we introduce the appropriate pet induction scheme. Well, I will avoid talking about this because it's rather technical, and I will pass to the next step. But here the idea is use van der Korput and try to decrease the degree of the family of variable polynomials. Okay. And what is how one continues from here? So assume that you have your good pet induction. That means that you will start working with this and you will decrease the complexity of the family of iterates. And in the end, you will get to something that is linear. And you will get a bound in terms of how many times you needed to run this. And you will get at the first, at the last step, you will get a semi-norm. This is like the semi-norms introduced by Bernard Host, because you will get in the end something like it's in linear it's essentially linear. And then here it's the same strategy as Wembo talked about. If you have an average control of semi-norms, then you can control this average by real a single box semi-norm. And from here to here is a lot of computation, but one can prove that by tracking correctly the coefficients that you get to some estimate like this, which was exactly what I mentioned in as the goal. The goal was to show that the original average, that one was 0 if something like this was 0. And well, after that, one can use enough ergodicity assumptions to replace this by these guys. Okay. Is there any questions so far? So that's the general strategy. Of course, I'm not giving much details, and there are some other steps in the middle, but I'm avoiding to talk about those. Okay, so what are sequences where we can apply the result? So we say that the Hardy sequence, this was introduced yesterday by Costas, but if you're not comfortable with it, just think of n to the or x to the 1.5. So it's a polynomial growth if it grows slowly than a polynomial. And this we use here a result by Richter, that whenever you have this, you can write your Hardy sequence as a part which is strongly non-polynomial. So this means that it doesn't belong as a polynomial. So we know that this is it will be of polynomial growth, but it is not comparable to the possible polynomials that could be compared. So this is a strong non-polynomial, and well, this is a yeah, that's the strong non-polynomial part, and the result applies whenever this dominates the logarithm. So if this is regular enough, we can apply our result, and so this is condition like this holds. I mean, when you have a condition like that, you have equidistribution. So it's a kind of natural to assume a condition like this, but we don't know if we can improve that to just saying that the function h it dominates the logarithm. But currently with the methods, we don't know how to push this condition to to this more general condition. And some other class of functions we can deal with are functions that are the sum of a Hardy and a tempered function. For instance, functions like this. The conditions, I didn't write them down, are a bit technical, but basically is that you will have such thing if, for instance, when the tempered function controls the Hardy one. So we have several conditions that one can check. We don't have in full generality what if all of them are good for our result, but we have several criteria that one can check in a particular example. Okay, so I think I went a bit faster than I expected, but okay. So let me give some problems or comments on what could be done. So a natural here, let me recall the result here. We have a single function A. One could ask what happens if we put several different functions? What kind of the things can be applied there? So this is a question that we're exploring right now with the CUTSA. And so we knew that we were all working the same thing. So why don't we settle this? And Andreas and Wembo and Costas. So we are trying to give conditions for this kind of expressions, which are more general than the previous one. So this is one type of direction one can push. Another direction is what happens when you don't have commutativity. And here there are a few very nice recent results. There is a result by Bergelson and Son with, I think, piecewise functions in the interval. There is recent results by Franziginakis and Host, when, as I think Sohail mentioned, when you have one that has zero entropy. So there are still things to discover in this setting. Personally, I have never tried to do anything non-commutative, but it seems that people can do things. And some other interesting direction is what happened about all of this in the topological sense. So this is what Chandong's mentioned in his talk. For instance, one could ask, and so what is the topological setting? Is you ask for your average. So in the measurable setting, you have the average that converges to the product of integrals. In the topological would be that you have a G delta set of points whose orbit is the whole product space. So what can you say in that context? So there are a few recent results that have appeared in this direction, especially the linear and the polynomial one, as Yandong mentioned. For a single transformation, there is result about nilpotent group actions with some weakly mixing assumptions, but pretty much there are many problems that could be explored, particularly for commuting transformations. So I think that's what I wanted to say. Thank you. Yeah, I practice this. Transitivity. I mean, yeah, there are some. So there are a few conditions that, for instance, the condition on the product space should be transitivity, but the single conditions of transformation should be minimum. But yeah, absolutely. Yeah, yeah. Topologically we mix. Yeah. Polynomial.